Okay. We skipped from chapter 4 or 5 to chapter 8. I thought because the material was, chapter 8 was prerequisite material for what we're going to study from now on. And the next exam is going to cover chapters 6 and 7. So we're going to do 6 today and 7 on Thursday. And we'll get started. Introduction to chemical reactions. It's a short chapter, so I'm going to take the end of the chapter after we finish the PowerPoint slides. I'm going to work out some balancing equations, because that seems to be a stumbling block for a lot of students. And really there's no substitute for practice, but it helps if you have some guidance as to where to focus your efforts. And I've got some pointers there also. So let's get started. The obvious question is, once we've defined what we think chemical change to be, how do you know that a chemical change is taking place? Sometimes you don't, right? But very often there are clues that a chemical reaction is in progress. And they range, right? We're basically bringing our senses to bear on the problem. What do we sense about the system that's being observed? Visual, of course, humans are visual creatures from the beginning to the end. So anything that we can see is pretty good evidence that we may have a chemical change going on. We're looking for particular signals. Those signals might be a color change, right? And I mean a definite color change, like from red to blue, or from pink to nothing. I'm not necessarily talking about adding a dark blue food color to a drink and it becomes light blue. That's just dilution. I'm talking about bona fide color changes. A solid could form, right? If you've got two solutions and you can see through them, and you put them together and mix them up, and now you can't see through them because a very finely divided solid has been created, suspended in that mixture. That's also called a precipitate. Or bubbles could form. If you form a gas, it's as long as you haven't introduced enough heat to boil the solution, that's a different process. But if you just mix two things together, or add two reactants together, and you get bubbles, and formation of a gas is a pretty good indicator that you have a chemical reaction. And then, of course, there's the appearance of a flame. If you see a flame, then there's definitely a chemical reaction. Or if you just sense a change in temperature. Now we're looking at different senses, right? The sense of touch. So you can feel the heat if it's strong enough, or you can touch it and feel a change in temperature, either an increase or a decrease in temperature. Then you probably have a chemical reaction going on. Here's an example of gas formation, right? So what do we do? Well, this is water, right? And we drop a 9-volt battery in it. Now, if you just drop it into pure water, this won't happen, because pure water is an insulator. It will not conduct electricity, and you need to get ions moving from one side to the other to carry that energy from one pole to the next. And when they do that, some of that energy is lost to the water. And in the process, bonds can be broken. So what happens is the water molecule, which is like this, that electricity breaks those bonds. And then, of course, you'll have two of these, and two of those oxygens come together to make one of those, and then two of these come together to make one hydrogen, but you have two of them, so that means you also have two hydrogen molecules. And that's all because of electricity. So we can see that a chemical reaction is taking place, and we can test the products of that reaction to see if that's true. If you take if you light a stick, we call them an ember, a specially treated splinter that we use in chemistry sometimes to test gases, and you light it and let it burn for 30 seconds or so, and then blow it out. It's still glowing. So there's enough energy there to start a reaction if there is material there to do it. And you just put that in that space up here, right here, and it'll pop. That's the hydrogen and the oxygen recombining in a combustion. Now that says that the gases produced are combustible. There's a fuel and an oxidizer. If you want to test the individual gases, then you need put a test tube over each one and catch the different gases, because one gas is going to be hydrogen and the other be oxygen. So if you collect the gases coming off of this pole, which is oxygen, and put that ember in there, then the ember will catch fire because oxygen supports a flame. But if you take that same ember and put it in the test tube that was collected over the hydrogen, then you hear a pop, because the hydrogen is interacting with oxygen in the atmosphere, and the ember is just an initiator. So you can get some clue as to what gases are being produced, what types of gases. All right, so in this case, bubbles are present. That's a sure sign that you have a chemical reaction. Here we have color changes, right? So in this case, I suspect we have an acid or a base. I can't tell from the picture. Oh, it's going to tell us, okay? We're adding hydrochloric acid. This is not an acid-base reaction, my mistake. Hydrochloric acid is coming out of this pipette, and the solution down here is cobalt-2 nitrate. In aqueous solution, cobalt-2 nitrate forms this pink or reddish color. But if you add acid to it, then you you trigger a chemical reaction. And the color change is the indicator. So we're not going to go into the details of what the reaction is, but take it from me, when you add that, you get, actually you get cobalt-2 chloride, right? Chlorine from here combines with the cobalt, and the cobalt-2 chloride is a different color than the cobalt-2 nitrate in aqueous solution. Water is intimately involved in this reaction. So the color change is the indicator here. Here's a precipitation reaction, right? You see this clear solution and you see this clear solution. When you add the two together, it gets cloudy. You're forming a yellow solid as a consequence of adding sodium dichromate, which is this solution, to lead nitrate, which is this solution. Precipitate would be lead dichromate. Right? So the formation of a solid is the indicator here that a chemical reaction has occurred. And by the way, once you've completed that reaction, you can filter that solution through the proper filtering mechanism, the right paper, and collect that yellow solid from the reaction, and just let everything else flow through, and then dry it down, and you have almost pure lead dichromate. Okay, so here's another possibility. Well, actually, this is an illustration of how we present chemical reactions in notation form. I used it up here, but I didn't explain what I was doing. By convention, we always put the reactants on the left with a plus sign in between multiple reactants. Right? You're going to have, you could just have one reactant. And in some reactions, that single reactant does something. It decomposes, or it rearranges or something, and produces products on the other side of the arrow. In this case, we have methane and oxygen burning to produce carbon dioxide and water. So that's your Bunsen burner in the laboratory. Natural gas is almost completely methane. There are some other products in there. In fact, there's one product that's added for safety. It's ethyl mercaptan, which is a sulfur-containing compound, because methane has no odor. So if you have a gas leak, you can't smell it. But with that mercaptan in there, that sulfur-containing compound, you pick that up in very, very small amounts in the air. So if you smell a gas leak in a building or in the laboratory, you're not smelling the methane, you're smelling the sulfur. Okay, so this shows the general arrangement, right? You have the compound written here, an element here, if it happens to be. So that's why I made so much, a big stink about learning how to write compounds in the very beginning, because I knew you were going to need them. You need to know how to write these compounds. Now this is a special one. It has a special name, methane. It's not, doesn't follow the convention that we've developed, type 1, type 2, and type 3 compounds. So this is an organic compound, and you're getting into a different nomenclature there. But that's the name of it. If we didn't know methane, we would call it carbon tetrahydride. But the accepted name is methane, of course. We know how to write oxygen, and it's a diatomic. Remember that? It's one of those elements that always occurs in pairs. Along with hydrogen, nitrogen, fluorine, chlorine, bromine, iodine. They're all diatomic. And then carbon dioxide, type 3 compound, and water, which has a special name as well. It's not dihydrogen oxide, which is proper based on our rules, but we still call it water. That's the accepted name. So you have reactants on one side, products on the other side. And in the process of writing the equation, this is what we would say unbalanced. So I have to explain what we mean by unbalanced equation. Okay. In a chemical reaction, we've known since Dalton's time, John Dalton, that atoms cannot be created or destroyed in a chemical reaction. They're simply rearranged. Actually, we've known earlier than that. Proust proposed the law of constant composition. Well, actually, it wasn't Proust that did that. It was Lavoisier that said that mass is the same for products as for reactants. What he meant was that no matter is created or destroyed. He just didn't understand at that time that it was due to the fact that atoms retain their identity throughout the reaction. When Dalton came along, he clarified that with his atomic theory. So, in order to obey this law, all the atoms that are present in the reactants must be present in the products and in the same numbers. That's what we mean by balancing an equation. The numbers of atoms of each element in the reactants are the same as the numbers of atoms of each element in the products. Okay. We'll talk about polyatomic ions in a minute and how you use those to balance. This is the author's idea of clarity, right? So if you have methane here, you've got 1 carbon and 4 hydrogen atoms, right? And here you got 2 oxygen atoms, and these are reactants. On the other side, you've got 1 carbon here, and you've got 3 oxygens. So it's almost as if we've created an oxygen. If we leave it as is, that's what you're implying. And also, we only have 2 hydrogens here, and we have 4 on this side. So that means we've destroyed 2 hydrogens if you leave the equation as is. But that's not proper. We have to balance the equation. So through a process that many chemistry book writers, authors, like to call balance by inspection, which is gobbledygook. It doesn't mean anything. But once the equation is balanced, you need to see that you can have 1 carbon, 1 methane, but you need 2 oxygen molecules in the reactants. And you need, you still only need 1 carbon dioxide, but you need 2 water molecules on the product side. And if you count up all the atoms, you find that, yeah, there are 4 oxygens on this side and 4 oxygens on that side. 1 carbon here, still 1 carbon over there, 4 hydrogens here, and now 4 hydrogens there. So now we're balanced, because they have the same number of atoms of each element on both sides. Now, how do you get there? Well, how do you represent that, right? We can't draw pictures for every reaction. That's very inefficient. So in the notation that we've introduced, reactants, arrow, products, we use coefficients, that is, prefix numbers, to each of the elements or compounds, as the case may be, in reactants and products, because the identity of this substance depends upon that ratio of carbon and hydrogen, or that ratio of 2 oxygens, or that ratio of 1 carbon and 2 oxygens, or that ratio of 2 hydrogens and 1 oxygen. So once the compound of the element has been written into the equation, you cannot change the identity of this reactant or product. So that means keep your hands off of the subscripts. Don't change the subscripts. But you can introduce coefficients, prefix numbers that tell you that, in this case, we need 2 oxygen molecules here, and we need 2 water molecules here. Right? We didn't change the identity. We just changed the number of molecules, which also introduces a multiplier on the number of atoms that are either in the reactants or products. Okay. So let's deviate from that for a moment and talk about physical states. The physical state of a reactant or product has a bearing on the type of reaction, the progress of the reaction, whether the reaction will even occur. So we need a notation for the state of the reactants and products. If the reactant or product happens to be a solid, we put a parentheses with a small s behind it. For instance, sodium chloride. We know that's a solid, so we just put a parentheses behind it with an s. Or if we're reacting pure water with something else, or we're just passing electricity through it, this would be a liquid. Or when we produce the hydrogen gas and oxygen gas from this process, that's what the G stands for. And if we were to balance this, of course, we would need 2 here and 2 here. You can count them up. That makes the same number of atoms on both sides. And then there's one other classification that is useful to us. There are a host of different states that you can introduce into a reaction, but we're only going to be concerned with these 4. The AQ means aqueous. So if we put that sodium chloride and dissolve it in water, now it's aqueous. Okay, those are the 4 most important for us. Here's an example. If we take potassium here, potassium's a metal. It's an alkali metal in the first group. It's extremely reactive with oxygen and water. So this liquid you see over the potassium in this tube is not water. That's mineral oil. Mineral oil excludes water and oxygen from the atmosphere. And that's the way you preserve your this highly reactive metal before you need to introduce it. Now, when you get ready to introduce it, you pull out a piece or however much you need, and you put it in water. So here's our water in liquid state. There's our potassium in solid state. And it produces hydrogen gas. Right? You can see hydrogen gas is forming here very, very tiny bubbles. They're not big bubbles like the previous slide. And then the KOH is a compound that's dissolved in the water. It forms from the reaction of potassium and water. In addition to hydrogen, you form hydroxide. Hydroxide, you know, is a polyatomic ion, but it's in solution. So we say it's aqueous. And notice this flame. That indicates that there is a reaction going on. So there's a flame, there's gas, and believe me, there's heat, lots of it. Because potassium and water, adding potassium to water is a violent reaction, extremely violent. So why is that flame there? Well, think about it. What's out here outside? Air, right? So there's oxygen. And what are you producing in your reaction? Hydrogen. So you mix that hydrogen and oxygen together at the surface of the liquid, and all you need is enough heat to get it started. And this reaction is so, we call it exothermic. Creates a lot of heat. It's enough heat to ignite the hydrogen in an oxygen atmosphere. Okay, so let's see, is this equation balanced? Right. Well, let's look. There's 1 potassium here. There's 1 potassium there. There's 1 oxygen here. There's 1 oxygen there. There are 2 hydrogens here, and there are 2 hydrogens here, and there's a hydrogen there. So we have 3 hydrogens. So that equation is not balanced. Right? We'll do one like it later when we get some rules to go by, some helpful hints as to how to balance equations. Okay, let's see, what do we got here? A challenge. When blue light shines on a mixture of hydrogen and chlorine gas, the elements react explosively to form gaseous hydrochloric acid. That's a misnomer. If it's gaseous, HCl, that is hydrogen chloride. It's only hydrochloric acid when you put it in water. So whoever wrote this slide probably didn't do well in chemistry. They were just hired to create the PowerPoint slides. So what is the unbalanced equation for this process? All right, so we've got a word problem here. And we need to extract information from it in the form of an equation. And for now, we're just going to write the unbalanced. So we need, what are the reactants? Well, let's see, hydrogen and chlorine gas, that mixture. So we've got hydrogen, and we know that hydrogen has to be diatomic. Right? That's another reason I wanted you guys to learn the diatomic elements, because when it says hydrogen, particularly hydrogen gas, you don't write just H. You have to write H2. Otherwise, you'll never balance your equation. And that's a gas. And then that reacts with chlorine, which is also diatomic, and produces what? Gaseous hydrogen chloride. Okay? So there we have our reactants and our products extracted from the word problem to give us this unbalanced equation. Right? So there it is. Now, how do we balance equations? We still have to observe Dalton's theory and the law of conservation of mass. That is, in a chemical reaction, matter is neither created nor destroyed. So in order to do that, we have to maintain the identity and the numbers of the atoms, elements in the equation. Okay. In the vast majority of cases, when chemical reactions are being observed, the chemists determine the reactants and the products experimentally. In other words, there's no guessing. You take the products, you know what you put into the reaction, right? That's given. But what comes out? What comes out, you have to identify it. Sometimes that takes a good bit of effort to figure out what the products are. Now, sometimes you can make an educated guess based on what you put in, what you think might happen, but there's no certainty until you've actually identified the products. There's one type of reaction that we may study. I can't remember if we study it in this. I'll point it out to you if we do. In which, if you're given reactants, then you should be able to write the products, because it's a particular type of reaction that only happens one way, right? I'm not throwing a curveball at you to see if I can trip you up, but there is one type of reaction that you can easily deduce the products. But for the most part, those products are experimentally determined. And then you be sure that you write the formulas correctly for the reactants and the products. And then once you've identified the compounds or the elements, as the case may be, once they're correctly written, their ratio of atoms in that substance is fixed, cannot change it. In other words, like I said before, keep your hands off the subscripts. So this is what the authors think is good advice. So I'm going to give it to you anyway. So you read the description of the chemical reaction, just like we did in that previous example. What are the reactants? What are the products? Are the states given? And then write the formulas for each of the compounds or elements. Okay? Then you put them in the form of an equation. Only a chemical equation is different than a mathematical equation. Mathematical equation has an equal sign. Chemical equation has an arrow, which progress from reactants to products. And later on, we may be introduced to an arrow that goes in the other direction, a double barbed arrow. Well, actually, it's a paired arrow, like that. So that just indicates that the reaction is capable of running backwards as well as forwards. But we're not gonna labor that point right now. That's just something down the road. So you write the unbalanced equation, right? And then you've got to figure out how to balance it. Now, balancing by inspection is a cop-out. You need some rules. You need some advice. Where do you start? What's a logical procedure? This is good advice, though. Start with the most complicated molecule and keep an inventory. So I'm going to show you how to do that in just a minute. And there's the author's idea of instruction. But until I show you what I call my budget, a balancing budget, then it'll all come clear. Okay, then of course you make a check at the end to see if it is balanced. You may think it's balanced, but until you actually count them up and prove that you have the same number of atoms of each element on both sides, then you can't be certain. And of course, once you've decided that your equation is balanced with the coefficients that you've chosen, then you look at those coefficients and say, can I reduce these coefficients any further? In other words, that ratio, those coefficients, 2, 4, 3, 1, whatever it may be, in front of each of the elements and compounds, whatever that ratio is, can you divide it by some other number and reduce it? You want the simplest whole number ratio of coefficients in your balanced equation. Right? So this is what, well, I erased it, but this is the balanced equation for the reaction of hydrogen and oxygen to produce water. You could satisfy the condition of conservation of mass with 4, 2, and 4 just as easily as 2, 1, and 2. And remember, there's a 1 in front of that oxygen. Right? If the oxygen's there, there's at least one of them. Right? So we don't write the 1. The 1 is there. Don't lose sight of that fact. So 4, 2, and 4 would be technically balanced, but it's not the preferred format, because you can divide the whole thing through by 2, and you can end up with a simpler equation. Okay, so these are some helpful hints that I've come up with over the years, and I did leave one out. I didn't have a chance to correct my slides, which was mentioned earlier. Start with the most complicated molecule first. The reason being that when you put let's say you have a really complex compound like that, ammonium phosphate. If you try to balance that later in the process, then any coefficient you put there is going to change the nitrogens, the hydrogens, the phosphoruses, and the oxygens, all four of them. So if you start early and get that one taken care of, then the simpler ones, when you introduce coefficients in front of something like this, like an element, it only changes that element. It doesn't change anything else, right? So that's why we start with the most complex one, unless there's some obvious reason to start elsewhere. And realizing that has a lot to do with intuition. In other words, you develop a feel for how to balance equations after doing dozens and hundreds of them. So here's the case where practice is not important, it's absolutely essential to mastering this technique. And if you don't have a balanced equation, you cannot proceed any further in chemistry. Like at the very beginning, if you don't know the symbols for all the elements, you're stuck. You can't go any further. Now you're at another crossroads. Well, actually we passed another one. If you can't write compounds correctly, then you're stuck. Now, if you can't balance an equation, you're stuck. So chemistry is one of those cumulative sciences. Actually, most of them are. They build on previous experience and stack it up. So you got to master each level before you can make it to the next one. Okay. So I'm not going to spend a lot of time on these rules because I want to show you. Right. So in the slides after this, there are more rules and more examples. And this format that's chosen is called my budget. I haven't seen it anywhere else. At least I haven't looked that hard either. I just developed it because that seemed the logical process to keep track of everything. So once you write your equation, your unbalanced equation, then you set up a budget so that you can track changes to the numbers of your atoms as you go. Right? So I mentioned earlier also that we try to balance elements last, because if you put a coefficient in front of the element, it only changes that one. Like this one right here, 6 in front of oxygen. Or also try to keep water to the last if you can. And it's not just for these general types of reactions, but there are some reactions in the future. I'm not sure if we cover them in this course, but you actually, when you're balancing an equation, you will introduce water into the equation. Otherwise, it won't balance. So we sort of keep water toward the end. All right, this other trick, I'll have to show you how that works. We want to make the coefficients all whole numbers, right? But that doesn't mean that we can't use fractions as an intermediate step to facilitate the balancing process. And if a fraction will work, then use it, and then you introduce a factor. Once you've got the equation balanced, then you introduce a factor like this 2 multiplier to get rid of the fraction. Right? So if you multiply 2 times 25 halves, you cancel the 2's and you're left with 25. Right? Those are the helpful hints. And notice the change, the change in background. What I tried to do is import slides from a different set, and they had a different format, a different background. But when I did that, the animations that I produced in what you can't see yet just completely fell apart. So the only way I could get them to work was to bring it over in the original format. So that's why there's a change from green to blue. Okay, so here's an example. And we've got this compound, ammonium phosphate, I mentioned earlier. Calcium chloride reacts with that to produce calcium phosphate and ammonium chloride. First thing you have to do is, especially if you're given this word problem, the named compounds, you have to write the compound correctly. So you have to know that phosphate is a 3- charge and ammonium is a +1 charge, and you need 3 ammoniums with parentheses, because these are polyatomic ions. Then calcium chloride, calcium is 2+, chlorine is 1-, so we need 2 chlorines. Calcium phosphate, with calcium 2+ and phosphate 3-, you cross multiply. So you take the 3 from the phosphate over here and the 2 from the calcium over here, and that balances the compound. And ammonium chloride is 1-to-1. Okay, now that we've got the compounds written correctly, we need to set up a budget. So that's what this is. So you have the element or group here, and you have the initial numbers here on the reactant side, and across that red line is the product side. So this is what you start off with, initial, and this is what you end up with, final. I've used another helpful hint here. If your reactants and products have polyatomic ions in them, look to see if the polyatomic retains its structure on both sides. So if you have ammonium here and ammonium over here, and it doesn't break up in the process, it doesn't break up into nitrogens and hydrogens and rearrange that way, then you can use the ammonium as a balancing group. It simplifies things a whole lot. Same for phosphate, right? The phosphorus didn't come apart and end up some other place. So the phosphate starts here and it ends here. So it stays the same on both sides. Then we can use this little trick to simplify things. Now we do an inventory, right? So we have 3 ammonias, right? We got that subscript of 3 ammonias. We have 1 phosphate, 1 calcium, and 2 chlorides. Okay, so we've identified all of our initial components. And what I usually do is add them up, right? 3 + 1 is 4, 5, 6, 7. We should have 7 elements or groups up here in the reactants. So we had 3, 4, 5, 6, 7, right? That's a verification that I've counted everything and we're starting from the proper position. Then we do the same thing for the products, right? There's 1 ammonium right over here. There are 2 phosphates right here, right? That's subscript of 2. There are 3 calciums right here. And there's 1 chloride right there. Okay, next thing you do is try to decide where do you start. So we don't have any elements here, so we can't hold anything till the end in reserve based on that hint. So we look for comparisons down here. Is there anything that's already balanced? Like, no, 3-to-1, 1-to-2, 1-to-3, 2-to-1, right? So sometimes you just start at the top, right? If you don't see any obvious advantage to starting anywhere in particular, just start at the top. So in this case, I'm going to balance the calciums first. right? So the first step, that's a little red 1. First step is to balance the calciums. So I need a 3 in front of this calcium to make 3 calciums, right? So that step changes that 3, that 1, to a 3. So now we have 3 calciums, but we've also introduced a multiplier times the chlorines, which means we have 6 chlorines now. So we make that change to the chlorines. All right. Now, by comparison, we still have these out of balance and those out of balance. Calcium's balanced, chlorine's balanced. Now that's for now. When you start trying to balance the others, you may influence previously balanced elements and have to go back and correct that later. So what am I going to do next? Well, let's see. We could have balanced the ammonias, right? So I've got 3 reactant ammonias. I need 3 product ammonias. So I put a 3, excuse me. Wait a minute, why did I put a 6 there? Because there are 3 on this side. I'm thinking that I'm going to put a 2 over here also. That makes 6 chlorines as well. Yes, that's what I'm doing. So I'm going to put a 2 there. Now, what I normally would have done is put a 3 here. But I've sort of skipped a step because that would have thrown something else out of balance, and I would have had to go over here and make 2 phosphates anyway, right? Because we need 2 phosphates on this side. So I skipped a step and I put 6 and 2 instead of 3 and left this in its 1, and then come back later and make this 2, and then have to go back over here and change that to a 6. So that cuts out a step. All right, so now we're balanced, right? And you can see, based on this method, 6-2-3-6, 6-2-3-6, you can see at a glance that you're balanced. You may want to go in and check yourself, you know, just add things up, see if it is balanced, especially if a grade depends on it. Or if you're later employed by a company and if you make a mistake balancing an equation, you could blow somebody up. You know? So there are serious consequences to doing it wrong. Okay, so let's take this one as an example and balance it using our budget. A budget for something this simple is overkill, really, but it'll illustrate the process. Okay, so we've got this equation, and I usually write, if I know it's unbalanced, I usually write the equation so I've got room, leave myself room to put in the coefficients. So we've got this one, right, is a solid, and then we're going to add oxygen to it as a gas, and it yields Fe2O3, which is a solid. Okay. Now this is given to you, right? So you don't have to worry about whether it's written correctly. You check it for yourself to see if the compounds are written correctly, but it's hard to tell because iron would follow the type 2 rule, and the charge is based upon the compound itself. So this iron would have a 2+ structure, 2+ oxidation state. And this one would have a 3+ oxidation state. And oxygen would have a 0 oxidation state. So that's neither here nor there. We'll talk about that again later. But now let's set up our budget, right? We don't have any polyatomics here, so we do individual elements. So we have iron, oxygen, and that's it. Those are the only elements we have to worry about. So on this side, we have 1 iron, and we have 3 oxygens. And on this side, we have 2 iron and 3 oxygens. Okay, we're going to leave oxygen to last because it's a free element. And anything we do to that only changes that element. So we'll keep it for last. But what we want to do is say, which one of these do we want to balance? Well, I'm inclined to start with iron, right? Because over here, oxygen occurs in 2 different places. So if we try to balance based on the oxygen, we're not going to catch both of them with 1 coefficient. But we are with iron. So we'll go iron here is 2, so we need 2 over here. Right? That makes 2 iron, and 2 plus 2 is 4 oxygens. Okay? Now, we've only got 3 oxygens over here. So the problem is you've got oxygen in 2 different places, and you've got it an odd here and an even totals over here, 2 and 2. So we could use a fraction, right? If we need to change this to 4, then we would need 4/3 here, but that would change this one. So we need a different tactic. We can use a fraction, but we don't use the fraction over here. We use the fraction over here, right? Instead of increasing this one to 4, why don't we decrease this one to 3? How about that? We use an intermediate step. So we'll have a half of an oxygen here, decreases that one back to 3, right? A half of an O2 is 1 oxygen. And then we got 2 here, makes 3. We got 2 iron, 3 oxygen. So now we're technically balanced, but we don't like fractions. So we get rid of that 2. So the way to get rid of fractions is to multiply everything through by the denominator. If that's a 2, we multiply the whole thing through by 2. Okay, that makes this 4. That makes this 1. And that makes this 2. So our coefficients should be 4, 1, and 2. Oh, what's the sum of the coefficients? 4, 5, 6, 7. Okay? Now I know that's a lot thrown at you at one time, but you got to start someplace. And it does illustrate the use of the budget and helping to, it's a decision process also. Using this budget, it helps you decide where you need to go. Because I looked at it at first like I wanted to go to 4 for here. But if I did that over here, that would change the iron also. And I could just be going in circles. So I said, well, instead of going up for that one, why don't I go down for this one? Because I can do it with just changing that 1.
For the exam too, I see it had some useful things. We could use those 3 papers: the common polyatomic ions, the periodic table elements, and the useful information.
Yes, if it's in useful information, you can use it on the exam.
Okay, because it was telling me to record my environment and stuff, and no papers were allowed. So I was just making sure.
Yeah, that's okay. No, you're all right. And
Okay.
it's going to, the expert system that runs Respondus, it's basically facial recognition. And it notices if other people come into the room. and it flags it. It rates the video of a student's test taking based on certain factors. And if your face moves out of the screen, like you're hunched over your paper and you can only see half your face, it's going to flag that as facial recognition. Or if you leave the room, it's going to flag that. And then it tells the instructor, based on low, medium, or high rating, whether it's worth investigating. So if it's a high rating, I'll go in and look at the video myself. And usually I'll see that, it's nothing to worry about. So I just pass it off and let it go.
Okay.
So it produces fewer flags if you're sure that your face is always in the picture.
So I should wait till class is over to take this, since we can't have like phones and stuff.
Yeah, that's right. Yeah,
Okay.
You should wait till after class, as soon as we're finished.
All
right. So if we balance this one, it could be, that would be the preferred way. I'm not going to go through this one in the budget because I'm making a different point. But that one would be balanced as well, and that one would be balanced. But the preferred one is that one. It's the simplest whole number coefficient ratios. And these ratios, once you balance an equation, those ratios are fixed. In other words, it's always 2 calcium oxides plus 5 carbons yields 2 calcium carbides plus 1 carbon dioxide. That ratio is permanent. No matter what you do to it, those ratios are fixed for a balanced equation. Okay, when you're balancing a chemical equation, which are false, well, subscripts in the reactants must be conserved in the products. No, the subscripts are only conserved once you've written the compound. Then you can't touch them. But you don't have the same subscripts in the reactants and products. Okay, so we found that this one was false. How about this one? Coefficients are used to balance the atoms on both sides. Yes, they are. When one coefficient is doubled, the rest of the coefficients in the balanced equation must also be doubled. Key there is balanced equation. Once the equation is balanced, then anything you do to the equation, you have to do to everything in the equation. Phases are often shown for each compound, but are not critical to balancing. That's true. It's rare that the phase matters. The only time it would matter would be if you had the same compound in 2 different phases in a reaction. Then you would have to consider one balanced separate from the other. Okay. These are just reminders. Right. Now, once we've got a balanced equation, what can you do with it? The whole purpose of balancing an equation is to describe the reaction. And once the reaction is described properly, then you can quantitatively conduct experiments, reactions, and you have a way to predict how much product will be produced. That's stoichiometry. Keep track of what goes in, and you can say what comes out. Or if you're expecting a certain amount to come out, you can say, how much do I have to put in to make that much come out? That's stoichiometry. All right. Oh, we're not going to talk about, we're not going to finish stoichiometry today. We just defined it. We'll get into that in I think, let's see, we got to go through chapter 7 and get a little more experience with types of chemical reactions in aqueous solution. And then when we get to chapter 9, we're going to talk about the stoichiometry again. So you don't have to worry about that until we get to chapter 9, which is a different exam. That'll be exam 5. Okay, so now what I want to do is practice balancing equations, because we've got a lot of time that we can use to do that. We've only been at this an hour, right? Just 26 slides and we're done. So let's get some practice balancing equations, and I'm going to pull these out of your review document. All right, so you'll see these again, and then when you get to the review document, you can look at those and say, I've seen that before. Let me see if I can do it myself. By the way, the worked problems that go with this review document are set up similar to that slide where I had the 1s and 2s and 3s above to show you the order. So if it says 1, that's the first thing I did. It says a 2, that's the second thing I did, right? So that you can see how the budget is built as you go along. Otherwise, you don't know what order the steps are. Okay, so I'm going to take this one. Let's see. Let's balance this equation. PCl5. PCl5. And we're going to leave the states out: solid, liquid, gas, aqueous. Let's see. In this one, plus this one. Okay. So what do we have here? We have phosphorus pentachloride, right? 2 nonmetals, type 3 compound. Water. This one starts with H. It's an acid. So that's probably in aqueous solution. It doesn't say, but that's probably what it is. And there's hydrochloric acid. It's probably aqueous also. Especially since you've got water here, then these are probably going to end up in solution. So we can say safely that they're acids. Let me see. That's, my easel has legs that walk. It moves around. Okay, so let's set up our budget. We have a polyatomic here, PO4, but we don't have it over here. It's just this phosphorus. So we can't use that trick with the polyatomics. We have to do individual atoms all the way down. So we have phosphorus, we have chlorine, we have hydrogen, and we have oxygen. So now, on the reactant side, we have 1 phosphorus, 5 chlorines, 2 hydrogens, and 1 oxygen. So that's 1, 6, 7, 8, 9. 7, 8, 9. And on this side, we have phosphorus 1, chlorine 1, hydrogen 1, 3 is 4, and oxygen is 4. Okay, so that would be 3, 4, 8, 9, 10. 4, 8, 9, 10. Okay, so that's where we start, from that position. So now where do we start from? We don't have any elements here, so we can't hold those in reserve. We might want to hold water in reserve, if that's possible. But we start with the most complicated one, right? It would be this one. But for this one, the phosphorus is already balanced. So let's see, how about chlorines are different. Hydrogens here, but hydrogens occur in 2 different places. So we probably don't want to mess with those right now. Let's take chlorine, right? So we'll say, if we got 5 on this side, we need 5 chlorines on this side. So that's 5 chlorines and 5 hydrogens. Well, 5 hydrogens and 3 hydrogens makes 8 hydrogens. So we have 5 here and 8 here. Okay. Now let's look at our oxygens. All right, we got 4 oxygens on that side. If we can get 4 on this side, we need a 4 here, don't we? So that makes 4 oxygens there. Now I'm breaking my own rule. I'm going to water right now. 4 oxygens and 8 hydrogens. And you'll notice from our budget, 1584, we're done. Now, if you find yourself trying to balance an equation and you go backwards and forwards, adding numbers here, 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 and it just goes on forever, the most likely case is that you didn't write your compounds correctly. If you don't write your compounds correctly, it will never balance, ever. So that gives us, and that's the simplest, right? There's a 1 there, 1 there, 4 there, 5 there. You can't reduce it any further. All right. So let's try another one. We'll do a few of these, and I'll probably let you go early anyway, because there's only so much of this you can do in class and before you get bleary-eyed. You need to do it on your own, really. Okay, how about yeah, let's do this one. Aluminum oxide. If I just said aluminum oxide, how would you write that? Well, we could say, I'm going to come over here a little bit. Aluminum and oxygen. Oxygen is 2 minus. Aluminum is 3 plus. So we have a 3 here and a 2 there. And then we're going to combine that with sulfuric acid, right? Sulfuric acid, no hydro in the name, so there's oxygen. So the sulfuric is a polyatomic derived from sulfate. Right? This is a 2 minus, this is a 1 plus, so you need 2 of them. Okay, and those react together to produce aluminum sulfate. Right? So if this is a 3 and that's a 2, we need a 3 over here and a 2 there. Okay? And then you also have water. Okay. So that's the unbalanced equation. All right. So let's see. Sulfate. Sulfate. So we can keep sulfate separate because sulfur doesn't occur anywhere else. It's only in this sulfate. So we can have aluminum. We can have oxygen that's not associated with sulfate. Right? And then we can have hydrogen and sulfate. Okay, so now our budget, we have 2 aluminums, we have 3 oxygens, unassociated oxygens. Then we have 2 hydrogens and 1 sulfate. So that's 2, 3, 4, 5, 6, 7, 8. 3, 6, 8. And on this side, we have 2 aluminum. We have the 1 oxygen unassociated. We have 2 hydrogens. And we have 3 sulfates. Okay, so that's 3, 5, 6, 7, 8. 1, 2, 5, 6, 7, 8. Now we have to decide where to start. Well, let's look at aluminum's already balanced. This oxygen is not, right? We could hold that. This one's balanced. Sulfate's not balanced. Let's do the sulfate first. Right. So we got 3 over here. We need 3 on this side. 3 sulfates. So that changes the sulfate. It also changes the hydrogens to 6. Okay. Now, let's do the hydrogens over here. Because we got 6 of them, we need 6 over here. So that's 3. Because that 2 times 3 makes 6. And it also changes the free oxygens to 3. 2, 3, 6, 3. We're balanced. All right. Okay, let's see. Let me find a little more interesting one. Keep going. Keep going. Okay, we'll do this one. We have iron 3 oxide. So a 2 here and a 3 there, because that's a 3 and that's a 2. Cross them over. And we react that with carbon monoxide. And that yields iron metal plus carbon dioxide. Okay. So let's set up our budget. We need iron. We need oxygen in 2 places here. And we need carbon. That's it. So we have 2 iron to start with. We have 4 oxygens. We have 1 carbon. We have 1 iron over here. We have 2 oxygens. And we have 1 carbon. Okay. So there's a free element. We're going to leave that till last. So now we want to look at oxygens because the carbons are already balanced in this scenario. So how would you get 4 oxygens on that side? You would need a coefficient of 2. 2 times 2 is 4. You've also changed the carbons to 2. Okay? So now we have to deal with carbon on this side. We need 2 carbons. So that makes 2 carbons here. And that makes, 5 oxygens here. Is that right? 2, 5, 6, 7, 8, 9. 5, 6, 7, 8, 9. Yep. 1, we have 2 plus 4 is 6, 7. 4, 5, 7. Okay. So how do we reconcile that problem? Well, I think what we're going to have to do is increase the number of oxygens by a coefficient here. This isn't odd. And that odd number combined with this even makes that odd. And when you get odds and evens on opposite sides, you have a real hornet's nest. So if we multiply this by 2, that changes that odd to an even. Right? So that gives us 4 of these. That gives us 6, 7, 8 oxygens. Okay? And still have 2 carbons. Right? So if we go to the other side, we find that to get 8 oxygens over here, we need 4 of these. So that gives you 4 carbons and 8 oxygens. So now we're stuck with this, because if we change that, we're going to have, well, let's just do it. If we change this to 4 to give us 4 of these, that makes 4 oxygens here plus 6 is 10 oxygens. Oh, iron's not a problem because we can fix iron right here. But I'm going round and round with these. I'm going round and round with those, and I think there's an easier way. In fact, I'm going to start all over again. Okay, that's 2, 4, 1. And 1, 2, 1. 1, 2, 1, 2, 4, 1. Okay. So I noticed that the carbons are only in one place on these sides. The problem is the 2 oxygens, they're in separate locations. So in order to, what we want to do, because the oxygens over here are always going to be multiplied by 2 and give you an even number, what we want to do is find a way to make even numbers out of these oxygens. So let's say if we multiplied by 2 right here, that would give us still an odd number. But if we multiply by 3, that would give us 6 oxygens. And then if we multiply this by 3, that would give us 6 oxygens. So I think I was starting in the wrong location. So if we make this 3 and this 3, that makes 3 plus 3 is 6 oxygens. And this makes 6 oxygens. So now what we've done is we've eliminated the odd problem with this right here. So what does that do for the rest of it? Well, now we've got 3 carbons here. Right? We got 3 carbons here. And now what we need is 1 more iron. Okay. That one had me stumped for a minute. I would have gone round and round and round and round and never ended up. And in this one case where it wasn't because the compounds were unbalanced, written incorrectly, it was because they were written correctly. And they threw this curve at us. So those types of balancing expressions, in fact, this one would balance much easier by a different method. Okay, and we haven't got to that point yet, where you balance electrons first. Notice that this one is a 2+ charge, right? 3+. This is a 3+ charge, but over here it's a 0 charge. So electrons have been transferred. So in these types of problems, it's more efficient to start with balancing the electron movements, but we haven't got to that point yet, right? So that makes them more difficult. But once you use, if we can use the redox balancing, which is the term for electron movement, if we use that balancing first and then finish it off, it would go a lot smoother. All right. Let me see if I can find another one to stump the band. Oh. This could be a challenge. All right. Let's see if this one is doable. Magnesium nitride. So remember, the pnictogens, when they're ionized, this would be the anion, that's the cation, that's the anion. They would be a 3- because of where they come from on the periodic table. So that means this would be a 2 and this would be a 3. Okay. Then you have water. And then we have ammonia, NH3. And then we have magnesium hydroxide. Okay. So now let's do our budget. Let's look. Nitrogen occurs here. That hydroxyl, we have to use individual elements. There are no polyatomics that are intact on both sides. So magnesium, nitrogen, hydrogen, and oxygen. Okay, we got 3 of magnesium this side, 2 nitrogens, 2 hydrogens, and 1 oxygen. 3, 4, 5, 6, 7, 8. 5, 6, 7, 8. And then magnesium here is 1. Nitrogen is 1. Hydrogen is 2 plus 3 is 5. Hydrogen is going to give us trouble because it occurs in 2 places. Okay, just a word of warning. And oxygen over here is 2. So let's see if we got enough. That's 5, 6, 7, 8, 9. 1, 4, 5, 6, 7, 8, 9. Okay, where do we start? Well, the most complex compounds here are the ones that have magnesium in them. So if we say 3 times this one, that will take care of the magnesium. Okay. And it will also change the oxygens to 2 times 3 is 6. And the hydrogens, it'll change from 3, let's see, 3 times 2 is 6, and 3 is 9 hydrogens. Okay? All right, so what do we have now? Well, we've got oxygens in one location, but the hydrogens are going to be a problem. So let's see if we need to deal with the hydrogens now. This, anything we multiply by that is going to be an even number because of that 2. So we need to get even number on this side somehow. If you've got 6 hydrogens here and 3 here, if we multiply this times 2, then that gives you 6 here and 6 here makes 12. And it also balances the nitrogens, because you need 2 there and 2 there. Now, in order to get 12 hydrogens, we need a 6 here. So that gives you 12 hydrogens and 6 oxygens. Okay, that one was easier than I expected. All right, let's see. We've got some others in here that could be useful. Yeah, this could be a problem. Let's try this one. Let's see, we're walking off camera there. There we go. All right. So this one is a reaction of, let's see, what is that? Propanol. That doesn't mean anything to you, I'm sure. But it's written like this. C3H7OH. It's an alcohol because of that group right there. And then we combine that with oxygen, which means we're burning it. And it produces carbon dioxide and water. There we go. Okay. This is going to have to be done atom at a time, element at a time. And we have this one element here that we can hold to the end. So let's see, we have carbon, hydrogen, and oxygen. That's it. So we have 3 carbons to start with. We have how many hydrogens? 7, 8. And oxygens, we have 2, 3. Let's see, that's 11, 14. So that's 10, 11, 12, 13, 14. This side we have 1 carbon. We have 2 hydrogens. And we have 3 oxygens. Okay. So let's see, that's 3, 4, 5, 6. 3, 4, 5, 6. Now where do we start? Well, let's see. How about the elements that are in here? There's 3 carbons there. Hydrogens and oxygens are already balanced. So let's say we want to make 3 carbons on the other side. Okay. That gives us 3 times 2 is 6, plus 1 is 7 oxygens. All right. How about hydrogens? Well, let's see. We need 8 hydrogens on this side. So if we say 4 times that, we have 8 hydrogens. But that changes the oxygens too. So we have 4 oxygens here and 6 oxygens there. So that's 10 oxygens, right? Six plus 4 is 10. So we got these. Now we need to come up with enough oxygens here to balance those 10. We've already got 1, right? So we need 9 oxygens. We've only got one at that location. And if we get 9 out of this one, then we can make 10 total, right? So how do you get 9 out of that? You take half a molecule times 9. So there's your 2. There's your 2 in the denominator. Half of O2 is 1 O, and then 1 O times 9 is 9 O's. Okay. Oops, sorry. 10. I forgot to add this one. So this 1 plus those 9 is 10. All right. So technically we're balanced, but we used a fraction to get there. So what we have to do is multiply the whole thing through by that denominator. Okay. So this becomes a 2. This becomes a 9. This becomes a 6. And this becomes an 8. 2, 9, 6, 8. All right. Let's see, 11:15. Let's look, see if I find any others that are, okay, there's one more. Let's do this one. So we're gonna react octane, which is the major component of gasoline in your car. It's a hydrocarbon. In other words, it has hydrogen and carbon. That's it. So C8H18 plus oxygen yields carbon dioxide and water. Let's see, I'm going to move this over just a little bit. Need a little more room here. There we go. Okay, now for the budget. We have carbon, hydrogen, and oxygen. All right, 8 carbons on this side, 18 hydrogens, 2 oxygens. We have 1 carbon here, 2 hydrogens, and 3 oxygens. Okay. Let's see, is that 5, 6, 1, 2, 3, 4, 5, 6. We have 8, 26, 28. So 18, 20, 28. Okay. So where do we start? Well, we've got carbon and hydrogens out of whack. Well, oxygen too, but it's odd even. And we can fix that odd even situation because this is an element. We'll save that one till last. But if we want carbon, 8 carbons over here, like that, then we get 16, 17 oxygens. All right. So how about hydrogens? Hydrogens are coming from this one. They're ending up in that one. So 18 over here becomes 9 over here, right? Makes 18 hydrogens. And 9 oxygens plus 16 oxygens are 25 oxygens, I think. Let's check it. Let's see, 8 and 16 is 24, 25. Well, no, that's it, 25. 2 times 8 is 16 plus 9 is 25. Okay, so that's right. And 18 hydrogens. Yep. And 8 carbons, right? Now we need to balance oxygens. And we can do that with this one and a fraction. So if we say 25 halves, that's 1/2 of this molecule is 1 oxygen times 25 is 25 oxygens. So now technically we're balanced. We're just not simplest whole numbers. So we get rid of that 2. So we have a 2 in front of here. We just do it like that, 2. And then that 2 gets rid of that. And this 2 makes that 16 and that 18. Okay? So that's your balanced equation for the combustion of octane. All right. The rest of this review document is dedicated to Chapter 7. So we'll get into that next Thursday. And for now, that's all I have. I think introducing Chapter 7 at this point would probably just, you need to practice balancing equations first. So do a lot of balanced equations. Then when we get to Chapter 7, the discussion will be a whole lot more meaningful because we are going to get into stoichiometry and learning how to track amounts of reactants into products and vice versa. Okay, so we're finished an hour early, and if you're so inclined, you can take the exam now.
Since we finished early, can I have help on this problem? This is on the homework on the OWL, and it's for balance of the chemical equations, and I was having a problem with these.
Okay. Oh, sure. We can take a look at those. All right, so we have SO2 and H2S yields S and water. SO2 and H2S yields S and water. Okay. So if we use our budget, that's where I would start. We have sulfur and oxygen and hydrogen. So we have 2 sulfurs and 2 oxygens and 2 hydrogens. So that should be 6. 1, 3, 4, 6. That's right. We have 1 sulfur over here. We have 1 oxygen, and we have 2 hydrogens. Okay, so we're going to hold sulfur to the end. Let's see. We're going to hold sulfur to the end and deal with oxygen and hydrogen first. So in order to get oxygens to balance, I actually need 2 over here. So that gives us 2 oxygens and 4 hydrogens. Okay? So to get hydrogens now to balance, I need 2 of these. So that would be 4 hydrogens. And now we have 3 sulfurs. Okay? So now to get 3 sulfurs, since we held sulfur to the end, that's good. We put a 3 here, and that makes 3 sulfurs. So that should solve that one.
Okay, yeah.
Let's see. You want to do another one?
Yeah.
Let's
Let me
see.
get my computer. They have this one too.
Okay. The second one?
Yeah.
Okay. So let's set it up with our budget. K2SO3, potassium, sulfite, barium chloride, yields barium sulfite and potassium chloride. Barium sulfite and potassium chloride. Okay. All right, so if we set up our budget for this one, we have sulfite on both sides, so we can keep that intact as a balancing unit. We have potassium, we have sulfite, we have barium, and we have chlorine. Right. So we have 2 potassiums, 1 sulfite, 1 barium, and 2 chlorides. Over here we have 1 potassium, we have 1 sulfite, we have 1 barium, and 1 chloride. 1 of each. Now, we don't have any free elements, right? So just nothing to be held in reserve. And they're all similar complexities, right? They're binaries, all binaries. So we can really start where we want to. And when in doubt, I just start at the top. So in order to get 2 potassiums over here, we need a 2 there. And that gives 2 chlorides. Okay? How about that? We're balanced already. That's the beauty of the budgeting system. You can see at a glance that you're balanced. All we had to do is make that one change, that one coefficient.
So they don't all always need a coefficient added.
That's the only way to balance.
Okay.
Yeah, the only way to balance is to add coefficients. You don't have any choice. I mean, after you've established the formulas for your compounds and written them in, they're fixed. They cannot change.
Mm-hmm.
You trying that other one?
Yeah.
Okay.
But I think I get it more now.
Okay. Like I say, as many as I've been doing over the years, I still get stumped like I was today. So the key for me as an instructor is to not give you those types that are beyond your abilities at the present time. And I think one of those was because I think it would balance much easier by a method that we haven't learned yet. So I need to try to minimize your exposure to those until we get to that point. Okay, I'm done.
All right. Well,
Yeah.
thanks for the help.
we'll reconvene in a couple of days. Yep, and we'll cover chapter 7 then.